Okay, sorry about that. I had to give myself permission on the other machine.
Oh, yes,
so today's talk will be given by Professor Dimi Culcer. I noticed, I think in March or February, I noticed his preprint on the archive. And the topic was very, very intriguing because it combines two subjects that are usually treated rather separately. One is semiclassics, and the other one is disorder. Because usually the common law is that as soon as you have disorder, semiclassical methods don't work. But of course, to understand, so if you open a physics textbook, if you want to understand conductivity properties in metals, you have to have a disorder to make correct predictions. And their work, so there's a joint work with Professors Atencia and New. Their work attempts to derive this from first principles. So this was very, very intriguing. So that's why I invited him to give a talk today. And yeah, so please, Professor Culcer, please, Dimi, please start. If anyone wants to ask questions, feel free to ask questions, to raise your hand during the talk, and then I can unmute you.
All right. Well, so it is very much a virtual pleasure to be with all of you today. Thanks for the invitation. And I hope that we can do this together sometime in the near future. So I've never quite given a seminar that's so specialized before, or on a topic that is so concrete. So I very much appreciate your interest, and I hope that I can make the next hour or so worth your time. This is the reference, which of course you guys know. And hold on a second. Here we are. So what I want to do in this talk is, first of all, I'm going to go over the semi-classical equations of motion as they were derived in this wave packet picture, then show how they lead to the Berry curvature, which has of course been one of their main selling points, how that leads to a calculation of the anomalous Hall effect, or at least one contribution to it. And then I'm going to argue that there are certain things that are missing there. And in order to understand those things, we had to go back to basically quantum mechanics, as Max said. Essentially what we did is very closely related to Kubo. So it's still, standard linear response, but it's based on the density matrix formalism. So I'm going to introduce, the philosophy of that and explain how we use that to treat disorder effects. And then finally, in the last part of the talk, I'm going to show how we go from this density, how we propose to go from this density matrix picture to the semi-classical picture and end up with a series of modified semi-classical equations. So this roughly follows the historical development of our mostly my thinking. Actually, when I wrote the outlook slide, I was thinking maybe there isn't much of an outlook, but then within 5 minutes, I realized that there's at least 5 or 6 different things that I want to look at in the near to medium future. So Max asked me before the start of the talk, what is, actually, what did you ask me? Sorry, I'm trying to remember.
When you got started.
Yeah, when we got started. So I got started on this kind of stuff in 2001. Then I spent my PhD on semi-classical dynamics. And then I abandoned semi-classical dynamics because I was traumatized by certain results that people got that clashed with it. And I had, we went in fits and starts, hoping to fix it. And it's only about 2 years ago that I realized how to fix it. Or maybe you guys will disagree, but that's why I became excited about this project. So please hurry me along if you think this is too basic. But this slide is about, how we see transport theory. And this is how I start a lot of my talks. There's a very simple, a very basic picture that says you have, you have a slab, then you have an electric field that accelerates the electrons inside the sample. And then you get scattering from various static and dynamic defects. And these collisions give rise to resistance. And then resistance is what gives rise to dissipation. So the electron is trying to get from A to B, from left to right. The electric field wants to get it there, and there's other stuff that gets in the way. Okay, and it's been, very many decades since people realized that this can be all captured in a nice, simple semi-classical theory, in which you look at electrons as wave packets. The wave packet belongs to one band. In the initial formulation, you simply had the velocity, which is the rate of change of the position of the wave packet. That is simply dE, the group velocity of the wave in that band. And then you simply take you combine this picture, which describes how electrons propagate between collisions. You combine this with the Boltzmann equation, and the Boltzmann equation is supposed to give you the effect of collisions. Okay, so you get dynamics from the electric field, and you get collisions having an effect on the distribution function. Okay, and so transport is, my opinion is that transport is inherently a semi-classical phenomenon. To describe transport, no matter what system you treat, you require some single particle description. That could be a very complicated quasi-particle, but you do need something to be transported. And you have to average over, degrees of freedom in real space and in momentum space. Now, the point of using wave packets, first of all, one of the reasons is that they're very intuitive. Another reason is, that charge carriers, we know that there's no such thing as a point particle. And the wave function has a finite extent in real space and a finite extent in momentum space. These, of course, have to be consistent with the uncertainty principle. And in transport, okay, we have to talk about trajectories. So we have to talk about where the particle is and where the particle is going. Okay. So we have a wave packet that is centered at RC in real space. Maybe you guys can see my cursor, and it's centered at KC in momentum space. And then we have a distribution of wave packets in as a function of RC and KC inside the sample. And then this distribution obeys the Boltzmann equation. Within the Boltzmann equation, sorry, maybe I'll just pause here and move on to the next slide. So the assumptions that the semi-classical model makes, which have been, okay for metals for a long time. So first of all, electrons are supposed to live in one band. Okay, so most of the time you assume that the electron lives in some band described by some index n, and most of the time you can actually drop this subscript. So the wave packet is going to be composed of a distribution of wave vectors centered around Kc, and the wave function is going to be given by this psi that I have at the top of the slide. This is the standard Bloch form where the U has the periodicity of the lattice. Okay, the wave packet is going to stretch over a few, so you can extend over a few unit cells because we always have to satisfy the uncertainty principle. And as long as we satisfy the uncertainty principle, then we can talk about change, about simultaneous changes in RC and in KC. So we can talk about where the electron is and where the electron is going, right? We assume that the external fields, so the electric and magnetic fields, are slowly varying. This is a standard assumption. And as I said, we have to say, we have to assume that the collisions are taken into account through the Boltzmann equation. And then generally, for all transport theories, we have to assume EF tau over H bar is much greater than 1. Okay, so basically KFL is much greater than 1, and L is the mean free path. So this is an assumption that is inherently built in the semi-classical model. Of course, so if you have to be able to talk about bands in the first place, but this assumption is not restricted to this semi-classical wave packet model, is what I'm trying to say. But the assumption is not restricted to this model of wave packet dynamics. In general, transport theories tend to make this assumption. If this assumption is not satisfied, then you're essentially in a disordered system, and then you're essentially opening up a can of worms. So now I wasn't planning to spend much time on it, but I thought that I would include a slide explaining how the semi-classical, the semi-classical equations of motion are actually derived. So there is this Lagrangian that was proposed by Dirac a very long time ago, where you take the wave packet and you sandwich this operator in between. So IH bar ddt. ddt is the total time derivative, minus h. So you sandwich it inside the wave packet, and then you use this Lagrangian to derive the Euler-Lagrange equations. And the justification that Dirac came up with was that when you work out, you treat the wave packet and its Hermitian conjugate as independent variables. And then the Euler-Lagrange equations actually for this W will reproduce the Schrödinger equation. In the Hamiltonian, you're going to have essentially the Hamiltonian evaluated at the center of the wave packet, and then you're going to have some gradient terms which describe, deviations around the center of the wave packet. There are things that I will not touch upon here, and I'm certainly interested in looking at them in the future. But I guess if some of you guys are working on semi-classical dynamics and you're familiar with Professor New's work, you will know that there is this orbital magnetic moment, right, which is important in a magnetic field and has been shown to be important in graphene and in transition metal dichalcogenides and so on. I will not discuss that here, but that also comes from those gradient terms. Okay, so you want to include electromagnetic fields into the wave packet dynamics. So you take your Hamiltonian, you make this Pyle substitution, and then you can add, you can also add a scalar potential. You ultimately have a choice as to how you include the electric and magnetic fields. And then you change, so suppose you will have a gauge potential. Then suppose you change K to K plus EA. Then your eigenenergies are going to be epsilon of K, so epsilon 0 of K, where K is now changed to the gauge invariant crystal momentum. And if you have if you consider an external potential, then of course you have to add that. And from the Euler-Lagrange equations, irrespective of your gauge choice, you will get the famous semi-classical equations in the form shown by Sundaram and New in 1999, where R dot is basically the group velocity minus this term that couples to K dot through the Berry curvature. And for K dot, you simply get minus the electrostatic force and then the Lorentz force. So I guess many of you will have seen this before. The Berry curvature is simply du dk cross du dk, take the imaginary part. And this was essentially the great novelty of New's approach. And this gives rise to a whole series of interesting terms in dynamics, which are still investigated today. Now,
excuse me.
Yes.
May I break you and ask you questions?
Oh, yes, please.
I'm very sorry that I am not expert on that topic. I'm wondering how do you deduce these equations in the last slide? That do you use the quantum mechanics formalism? I mean,
you mean
here
the semi-classical equations?
Yeah, I mean, first of all, in the second line, you replace the Hamiltonian by the Hamiltonian as k plus EA over h bar minus EB.
Yes.
And second line. So, I mean, this is
so this is a standard, right? In I think all condensed matter approaches. So you have to I mean, we're doing ultimately non-relativistic physics, right? So we have to change the. Let's suppose that we have a magnetic field and an electric field, and let's actually.
I'm sorry, but in the second, so do you assume you are having the system under the magnetic field?
Yes.
I mean, in the last slide, as I remember, you said you are not discussing the effect of magnetic field in the last slide.
Oh, sorry.
You are ignoring the gradient term.
Yeah, I just wanted to show it. You're right. So I just wanted to show the semi-classical equations in their full glory.
You are just talking about the general theory.
Yes, the general, and you are right.
Okay.
However, I should say that the gradient term, so those gradient terms here, yeah, so they give rise to an extra correction to the energy, but that correction, I mean, it won't show up in the semi-classical equations. It has to be evaluated separately.
Okay. I see. So just one. I want to have just last question. I mean, to deduce the equation for the last line. I mean, semi-classical equation of motion. You are doing, kind of considering the quantum expectation value of the position operator or energy operator, so on, so that you are kind of discussing the general theory by using the quantum mechanics. I mean, starting from the Schrödinger equation, that taking the product between some psi and taking some quantum mechanical expectation that you can deduce these equations. Is it? Do I understand, or I mean?
Yeah. So it is really. It's really based on this. I would actually call it a mixture of classical and quantum. That's, I guess, partly that's, why they call it semi-classical. But you would take this wave packet, and of course the wave packet is just, you know, some spread. Let's just presume it's some Gaussian, you know, multiplied.
Coherent state. Okay.
Yes, so something like that.
Okay.
And it's multiplied by some, you know, the Bloch wave function.
Yes.
Right. And then you treat this wave packet, this W that I have here. You essentially take W and W dot and construct the Lagrangian in terms of W and W dot. Sorry, just 1 second. You evaluate, it's okay, there is a quantum mechanical expectation value. There is an expectation value of the position operator involved here. And that's right. So at the end of the day, you do have to evaluate, let's go back, this wave function here, right? You have to evaluate psi r psi, where r is an operator.
Yes.
And you get the standard expression for the position operator between Bloch states,
Mm.
okay, which is the ddk of a delta function, and then this gauge connection, right? U, I, du, dk.
Mm-hmm.
And then at the end of the day, you also have this, this like, let's say Gaussian type distribution, this yellow type distribution over here, that multiplies this quantum mechanical expectation value that you mentioned. And then you get the expectation value evaluated at the center of the wave packet.
Mm-hmm. Yeah, I think I understand.
Yeah.
Yeah, I mean, I see how to compute it.
Yeah.
Okay.
And I have some extra slides that I can send you on this. I just, because, we have to, eventually we can't go on forever. So I decided to take some of the details out, but, yeah.
Yes, I see. Thank you.
Thanks. All right. So, you will have, this Berry curvature, of course, an important quantity. When is it non-zero, right? We have this equation of motion. And of course, if we look at what the left-hand side and right-hand side do under time reversal, R dot, of course, changes sign under time reversal. 1 over K, of course, changes sign under time reversal. And K dot doesn't, because K changes sign and ddt changes sign. So whatever we have over here, okay, has to change sign under time reversal. This also means that if I take omega of minus K, I will get minus omega of K. All right. There's some other remarks about the Berry phase that I think we probably don't need at this stage, but we can go back to them. And once more, to continue the symmetry argument, suppose, right, so we said that we need time reversal invariance to be broken. So omega of K itself, even if time reversal is preserved, omega does not necessarily have to be 0. However, when time reversal is preserved, we have Cramer's degeneracy. Okay, so E of K is E of minus K, right? So we may or may not break time reversal. Sorry, we may or may not break inversion, right? But Cramer's degeneracy says that if the state at K is, if the state at Kc is, sorry, if the state at K is occupied, then the state at minus K is also occupied. So then when we integrate, if we integrate over all filled states, this has to vanish, okay? This integral has to vanish, because if time reversal is preserved, right, we cannot have this like a net Berry curvature. So if we have an effect that actually depends purely on this omega, okay, this thing will have to vanish. And this is kind of important. All right. So this, so far, is the semi-classical, is the wave packet part of the dynamics. Okay. Now, the wave packets are assumed to follow some distribution, f of RC, Kc, and time. And this distribution will obey the standard Boltzmann equation. So you can just think of them as, semi-classical particles. And this is just, standard, last year undergraduate statistical mechanics, the way I do it. This J is, I usually call my scattering term J. And in the relaxation time approximation, we can always say, this is F minus some F equilibrium divided by some relaxation time. And if we're talking about electrons, then usually the equilibrium distribution is going to be the Fermi-Dirac distribution. Of course, there's a lot of research about how things thermalize, what the real equilibrium distribution is in the general system. I'm going to say, let's keep things simple. And let's just assume it's Fermi-Dirac, and that is actually complicated enough. So if we have an electric field applied, we're out of equilibrium, then we can say the distribution function is the equilibrium function plus something else, some non-equilibrium correction. and this correction is solved to linear order in the electric field. We're going to say the system is homogeneous, so we're going to make all the approximations that we can. We're going to say there's no magnetic field, and then K dot is just going to be minus EE. Okay, so that is again purely from the semiclassical equations. And then very simply, you can get the textbook results. You know, this gives you the Drude conductivity. The correction to the distribution function is this thing EE tau over H bar, and then just the derivative of the equilibrium distribution with respect to K, right? So this is all very standard textbook stuff. My favorite reference is Michael Marder's book, but you can probably find, you know, 100 other textbooks that deal with this. So the F equilibrium dk, if you F equilibrium is only a function of the energy, right? So it only depends on K through the energy, then you're going to have dF dE, and dF dE, if you're at low temperature, is on the Fermi surface, okay? Because it's, if you're at low temperatures, then this is going to be a delta function at the Fermi surface. So essentially, this is responsible, this correction to the distribution function is responsible for a Fermi surface effect. So what do we do now? We say we want the conductivity. The conductivity is going to be given by the velocity. So minus E times the velocity, that's the current due to any one carrier. So the velocity R dot is the group velocity plus this Berry curvature correction. And note that here, remember in the actual equation, it was K dot. And now I've already substituted for K dot, I've put in EE over H bar. So I have this term in the actual particle velocity, which goes as EE cross omega. And then the distribution function is the equilibrium distribution. And then this correction, which is due to the Fermi surface dynamics and the scattering. All right. Of course, the term that doesn't, if you work out the expectation value of the velocity, strictly speaking, you have to multiply. So you have to multiply these two together and then integrate over K. Of course, when you multiply, you take the velocity with the equilibrium distribution function. That will integrate to 0 because there's not going to be a current in equilibrium. And there are, for terms linear in E, there are two possibilities. So this guy here, the group velocity multiplied by the correction to the Boltzmann equation. So that will give the Drude conductivity, which depends on tau. So that will give you the standard NE squared tau over M. And there is this other term, which contains the Berry curvature. And because I already have an electric field factor in here, then I have to multiply by the equilibrium distribution. And again, this is an artifact of the way that the theory is constructed and the way that we're doing perturbation theory. Right, and this term here is independent of scattering, and it gives some contribution that doesn't contain tau. Okay, so it can be evaluated. There's, you know, there's a reason why all the computational guys love this, because they can evaluate it purely from the band structure. You have the band structure, you can evaluate the Berry curvature, and lo and behold, at the end of the day, you get this intrinsic contribution to the conductivity. Now, okay, so this I've already, maybe I'll skip, so I've already discussed. And then this intrinsic term is going to be F equilibrium and then E cross something, cross the Berry curvature, right? Of course, the omega breaks time reversal. And since it is E cross something, it has to be Hall. It has to be transverse to the electric field, right? This is not the ordinary Hall conductivity. We don't have a magnetic field, right? There is no Lorentz force. So this thing is important when there is, you know, when the system already breaks time reversal. In the equilibrium case, so when you have a magnetization present, the magnetization doesn't give you a Lorentz force, so it gives you something else, right? You get a Hall effect that doesn't have where there's no external magnetic field, and this is why we call it the anomalous Hall effect. By the way, I also have a review of the anomalous Hall effect that came online just a couple of days ago, so we can also talk about that at some point, maybe. So, we can look at a system where this is important, right? Where this is relevant, let's say. So we can look at our beloved Rashba model. In the Rashba model, we have, so for a semiconductor, we have the scalar dispersion. Then we have the spin-orbit interaction. So this is a two-dimensional system. Spin-orbit interaction, sigma xky minus sigma ykx. And then we have to break time reversal, so we're going to have some exchange field. Let's just pretend this is some magnetization, okay, which is pointing out of the plane, so perpendicular to the plane. So you look at the dispersion of this, and you get two bands. This splitting is basically the splitting due to the magnetization, and one of them is basically parabolic, and the other one has this Mexican hat shape. Okay, in a semiconductor, you actually have to be at, despite the way we plotted it here, you actually have to be at very, very low energies to be able to observe this. So I think that if you actually put the Fermi energy here, where we have it, if you want to put the Fermi energy here, in a semiconductor, it's actually incredibly difficult to do it, but that's just a detail. So the Berry curvature, you plot it as a function of wave vector, and then lo and behold, it's this spike at the wave vector is 0. So it looks like a monopole, okay, and this is why people say that the Berry curvature is a monopole at the origin. So in general, it's a monopole, but for other models, it's not centered at the origin, right? It might be centered at some other wave vector. The point is the Berry curvature is a spike. So to get the conductivity, we simply have to, in this simple system, the electric field is going to be in the plane. You work out the Berry curvature, and the Berry curvature only has an out-of-plane component. And then to get sigma xy, the whole conductivity, you just have to integrate the Berry curvature over these occupied states. And if you somehow, I'm going to go back to the previous slide now, if you somehow manage to occupy only this lowest band, and somehow to make this splitting very large, and then you're able to go to large wave vectors, if you can, under any circumstances, extend the limit of integration, so to go from 0 to infinity, or actually to the edge of the Brillouin zone, then you're going to get a quantized conductivity. You're going to get a Berry phase of pi, and this is going to give you E squared over 2h. Okay, so that will be a quantized anomalous Hall conductivity. Or so the theory goes. Okay, there's a slight problem with this, which is we haven't, okay, I'm perhaps lying here when I say we haven't taken into account disorder at all, but you see that the theory is constructed in such a way that, the disorder only appears in the Boltzmann equation. And in this Hamiltonian, where we constructed the wave packet, okay, we didn't say anything about disorder. So if you want to take into account disorder properly, then you have to do, as Professor Nakano said, you have to do quantum mechanics. Okay, so the calculation actually was done by Molenkamp's group. And this was actually, I mean, you guys might be aware, this was all started by Professor Inoue from Tohoku. So there's the famous collaboration, Inoue, Bauer, and Molenkamp, who first of all, actually showed a very similar thing for the spin Hall effect in 2004. And then they wrote a similar paper for the anomalous Hall effect in 2006. Okay, and then other people recovered this result. Okay, so if you take into account the disorder, and you consider this system in which you now, let's say, you take the Fermi energy and you go to, a realistic Fermi energy, which is going to be quite, is going to be quite large. So both bands are occupied. Then disorder actually kills this Rashba contribution to the anomalous Hall effect completely. All right, and I'm going to tell you fundamentally what the problem is, and this is going to be more, it's going to be more obvious when we move on to the density matrix side of things. So all transport theories assume that there is this small parameter EF tau. So there is, sorry, this large parameter EF tau over H bar. So KFL, where L is the mean free path, this is much larger than 1. All right, so that means that 1 over this parameter, so 1 over KFL or H bar over EF tau, that is much smaller than 1. And this is our small parameter. This is the small parameter in terms of which we formulate our expansion. All right, so our theory is really an expansion in this small parameter. However, the first term that appears in our theory, with or without the Berry curvature, the first term comes from this correction to the distribution function, and it goes, it's linear in tau, where tau is the scattering time. Okay, and tau goes as if we think of some collection of impurities, and there's some impurity density, N impurity or Ni. Okay, the tau is going to go as 1 over the impurity distribution. So we're making an expansion in the impurity density. So we're making an expansion in the impurity density, but the first term in the expansion is the impurity density to the -1. So now, if you're familiar with transport theory, you'll know that there's a very good physical reason for this, which is that you start with your equilibrium distribution and you turn on an electric field, and the electric field shifts the Fermi surface, right? So you have an equilibrium Fermi surface, which we can think of as a sphere or a circle. You have the electric field, and the electric field shifts this thing. And the shift in the Fermi surface is proportional to tau, right? And if tau, if there is no impurities or no phonons or nothing to scatter, there is nothing to keep the Fermi surface near equilibrium. So the fact that this expansion goes as linear in tau and 1 over the impurity density is actually for a very deep physical reason. All right, so we want to understand how to actually incorporate disorder properly. So there is this treatment by Inoue-Bauer and Molenkamp. And this is all in terms of Kubo. So we know that contains disorder, it's taken into account properly, but that is also essentially, there is a cookbook for doing these things, and it's not immediate, that they showed that it was the vertex correction that killed it, but there was no, physical interpretation for it. And I think I think this statement is correct. We know the theory will give you this answer that it's 0, but and we know that there's going to be some correction, okay, that there might be some correction of order 0 in disorder, okay, but it's fair to say that nobody really understood what was going on. Okay, so I really like this density matrix idea, first of all, because the Kubo formula, as you all know, starts from the density matrix. Okay, so all this linear response ultimately goes back to the density matrix. But there are other ways to formulate linear response theory, which make the approach much closer to the Boltzmann equation. Okay, so I'm going to try to discuss this hopefully a bit faster in the next 10 or 15 minutes. Okay, and then hopefully I'd like to go back to, so I'd like to cast this density matrix picture in a way in which we can recover something that looks like the semi-classical equations. So we can go back a little bit. And now we're going to say that we have a Hamiltonian that contains a band Hamiltonian. We're doing quantum mechanics now, right? There's EE.R, constant uniform electric field, and there's a disorder potential. The magnetic field is set to 0 for now, and it's going to be set to 0 until the end of the talk, okay? Now, the central quantity that we're looking for is the density operator. And once we project that onto a certain set of states, we're going to get the density matrix. And of course, the important stuff to remember here is that the density matrix, it contains everything. There is no separation between the dynamics and the distribution, right? The density matrix is something that you calculate as the solution to an equation. Later on, you sort of sit and think about it, and then you try to extract what the dynamics are. So we have to solve the quantum Liouville equation. Again, this can be written as an operator equation. I think this should be a partial, so I apologize. And the H is going to contain everything. So then I'm going to say, of course, in transport, we have to, the only sensible way that we can deal with this random disorder, disorder potential, is to average over disorder realizations. So we're going to take the density matrix and we're going to say, okay, we're interested in the impurity average of this thing. And we're going to take the impurity average and single it out. So there's going to be, and that's the row brackets over here. Everything else we're going to call something that's called G. And again, I'm using my own notation. And I realized I've used this G, 10 slides ago, but yeah, there's only so many letters, so I apologize. And this G here is something that we're going to get rid of. Okay, because the point is, we're going to take the Liouville equation and we're going to break it down, and we're going to get an equation for this row average. So averaged over disorder, and that's what we're interested in. And we are going to get an equation for this G. And then these equations are going to be coupled, and we're going to be able to integrate over this G, which is the fluctuating part, okay? And the way we do this integration, or the way we make this approximation, that defines, the level at which we treat disorder. So I'm just going to focus on Born here. And, the approach can be extended. You can do self-consistent Born, you can do the T matrix, you can even cover the Kondo effect, you can cover weak localization. So we have papers where we've either done this or we're doing it. So the approach is systematic, right? So at the end of the day,
excuse me.
Yes, yes.
Just 1 second. And I mean, the first line, you are writing that the bracket of row is diagonal in wave vector.
Yeah, so that's not, that is,
just wondering why.
It's not a strict assumption,
yeah.
But in if the so that is not, it's not necessary for anything that comes afterwards. But the reasoning is in the same way that the impurity averaged Green's function is diagonal in wave vector. So you start with a lattice which you assume is perfectly periodic, right? And then you throw on top of it, you throw this random function. Okay, of course, the random function does not have translational periodicity.
Right.
All right, but then you say you average over disorder. So you take this average over impurity configurations. Then by taking the average, you're essentially replacing the disorder or the expectation values by this, uniform gunk. Okay, so now that you're making you're replacing this with some uniform thing, then you're recovering translational periodicity. So you're expecting rho to be diagonal in wave vector.
Yeah, intuitively I understand very well.
Yeah.
And I mean, I'm just wondering, it is possible to qualitatively justify this statement?
Well, so it also, I mean, that also comes out when you know, we don't, so you can go through the algebra without assuming it. Okay, and then you work out the scattering term, and the scattering term turns out to be diagonal in wave vector as well.
I mean, just okay. So just last question to deduce the last and to deduce the equation of J of bracket rho. I mean, the equation in the last line. Yeah, last line. J. Is it you don't need the assumption that the diagonality of rho.
You do not.
You don't need this assumption to deduce the final equation here.
You don't, because you see, yeah, so this is, of course, there are very many brackets here, so I appreciate that, you know, so this whole thing is average. Can you see my cursor?
Yes.
So there's a bracket all the way outside, okay? Now, of course, this row is already averaged. So really the bracket only acts on the disorder. Right, the H0 is the band Hamiltonian, so that has nothing to do with the disorder. So at the end of the day, we will only get the average of these U squared. Right, and the U squared, there is a formal way to carry out this average. Right, and then when you take this average, then it will be diagonal in K. So U is not diagonal in K, but U squared average will be diagonal in K.
Okay, I see. Thank you.
Yeah. All right.
If I may, this is maybe a subtle question, but usually when you do these derivations, they depend on the initial / equilibrium state. So for example, if you seem to be considering a 0 temperature state for a lot of your talk, which is perfectly fine, but of course you can also consider finite temperature states.
Yeah.
And what I'm saying is that this row average, in some sense, this should correspond to your equilibrium distribution, and you have to make a choice here, right? So what kind of assumptions do you make on row average? So for example, if you add a linear electric field, you know, you are driving the system out of equilibrium, you know, even if you ignore the fluctuations. So you have sort of two small parameters. One is tau, or you can also use the length, the typical length scales between scatterers or something like that, and the other one is the electric field. And so you seem to be making expansions with respect to two small parameters, and this seems to be a bit subtle, no?
Yeah, I mean, so right now the electric field has not been added, but there is, okay, so let me add something to that. So right now on this slide, we're in equilibrium. Okay, and you're right that the form of the equilibrium density matrix matters. Now,
yes,
if I stick to the Born approximation and I assume the scattering is scalar, then if my row average here, you know, the criterion is that rho should kill this entire equation. If I take a density matrix, which is simply composed of the Fermi, so it's diagonal and Fermi-Dirac distribution, you know, as you would do if there is disorder, then this term would vanish, and then there is no time dependence.
Yes.
Now, if your disorder is scalar and you plug in the you know, your Fermi-Dirac, you know, distribution here, and that will also kill this integral. Okay, so then I will continue to take, so in the Born approximation, I will, and that's true for a multiband system as well, right? So in the Born approximation and for scalar scattering, like Coulomb impurities or delta function or whatever, then a Fermi-Dirac is enough for this. However, it's actually an important question, because if I have skew scattering, so I don't know if you've looked at this in the past, but let's say the potential has some spin dependence. Okay, then Fermi-Dirac is not enough, and I have to, I have to look for some other small I have to introduce a third small parameter, or try to solve this in some other way. So if my potential had a scalar part and a spin part, then I had better be hoping that the spin part was smaller and I could do perturbation theory in it.
Yeah, of course. Otherwise, your ansatz breaks down. Yes.
Yeah. All right.
Okay. Thank.
Yeah, my pleasure. So if I turn on an electric field, okay. So I'm sorry, I used J naught here for the Born approximation scattering term. I will, so V is going to be my electric field driving term. And I need to make a correction to the scattering term, right? So right now I have not expanded yet, but I will shortly. Okay, and I have to make a correction. This correction is actually important, and we only realized about a couple of years ago that it is important. So when you turn on the electric field, you actually need to add the electric field, the electrostatic potential, you need to add it into the time evolution operator, and that will give you a correction to the scattering term. So if we think now in terms of this linear response philosophy, then everything on the right-hand side is linear in the electric field, and everything on the left hand. So I can substitute here rho equilibrium, and I can substitute here rho equilibrium, and over here I will have rho steady state, which is linear in the electric field. So again, this is like basically, so it's linear response, and it's also kind of similar to the Boltzmann equation, except you have this extra term with the commutator of the band Hamiltonian with the density matrix. So that takes into account the multi-band nature of the problem. Now it's interesting, actually Alan MacDonald was the one that suggested, I'd been using this formalism for many years, and I was mostly interested in spin problems. So I was always working in the Pauli basis, with the spin eigenstates 1, 0 and 0, 1. And about 6 years ago, Alan MacDonald suggested, that we do a version of this theory in the eigenstate basis. And in the eigenstate basis, it actually looks very interesting. So if I look at this driving term, rho 0 is going to be my equilibrium density matrix. I can deal with this electric field in a straightforward manner. I have a diagonal. I can decompose it very straightforwardly into a term that is diagonal in the band index, delta mm prime. So m is the band index. And that's just the Fermi-Dirac distribution for each band, and ddk of that. That's the Fermi surface contribution. And then I can get a contribution which is completely interband. You can see that it depends on the occupation of the bands, right? F0 band M, F0 band M prime. So if the bands are the same, this thing vanishes, and this thing is mediated by none other than the Berry connection, right? The Berry connection, so UDK. In general, it can have off-diagonal elements. And if I think of the Berry connection for a single band, then I take del cross K, so the cross product of that in K space, with that in K space, then that's the Berry curvature, right? So this tells me that this density matrix formalism has a very nice decomposition into a band diagonal part, which contains the Fermi surface dynamics. And it also has a band off diagonal part, which contains, basically all the topological stuff goes in there, right? That's the short way to put it. And that it's basically, at least at first sight, it's the Fermi C effects, because it's F0 rather than dF0 dk. So there is, let me maybe skip this. Okay, so because I've just said that I have a driving term that can be broken up into two parts. So then it makes sense to take the density matrix itself and to break it up into two parts. And I just want to focus on this equation. So I'm going to take the density, this average density matrix, and I'm going to say, well, I've got basically a charge density in each band. So a diagonal term, which I call n, and I've got a term that has all the interband dynamics. Right. So in this S, which is like a pseudo spin, I say that M is not equal to M prime. So the Hamiltonian, the band Hamiltonian H0, right? This one is going to be diagonal in the band index. That's the whole point of being in the eigenstate basis. So this N is going to commute with the Hamiltonian. So the N, unsurprisingly, represents the fraction of carriers that remain in eigenstates. And later on, in very shortly, we're going to see that this contains the Fermi surface response. It commutes with the Hamiltonian, so when I write down my effective equation for n, right, I'm not going to have that commutator term, and it's actually going to look exactly like the Boltzmann equation. And then I have to decide what to do with this S. So I have to solve this to see what this S does. Right? So obviously the scattering term is the key to everything. So I want to break stuff up into a diagonal part and an off-diagonal part. And at the beginning, it's going to be straightforward, but then of course, as we keep building up this expansion, it's going to get quite difficult. So this is my scattering term in the Born approximation. And I can say, I can break this up into something that go into a band diagonal part and a band off diagonal part. Now, of course, the rho itself has a band diagonal part and an off diagonal part. So there are going to be cross terms, but we're going to deal with those in a minute. All right. So J diagonal, I take the N and I work out, I take N, I don't make any assumptions about N. So I don't say it's equilibrium or out of equilibrium. I simply say it commutes with H. I plug in N here. I evaluate what I get, and then I take the diagonal part. All right. What I get without any effort is exactly Fermi's golden rule. And then I also look at the off diagonal part. All right. And the off diagonal part has some terms that contain essentially interband scattering, okay, which scattering between the bands, which contain the distributions due to different in different bands. Now again, so there's another assumption here, which is that something I've made later, that the scattering is elastic. That's not an important assumption. So the generalization to phonon scattering is very straightforward. You just have to add or subtract the phonon energies. So the scattering term, this guy basically keeps the Fermi surface near equilibrium. And then this guy, out of the terms that we've investigated so far, this induces, I said here, coherence. It's really transitions between the bands, okay? So when I discussed with Professor New is not so keen on using the word coherence. It's more like a band mixing, okay? So there's transitions between the bands, but there's also some band mixing that is induced by the disorder. So the solution, okay, we said it's an expansion in EF tau. So I've already, but this is really the key to everything. So if this slide doesn't make sense, then please ask. Okay, let's look at this equation. All right. So I said that we start from this, kinetic equation here. All right. And I say, let's look at the diagonal term. So I'm going to have partial and partial t, and I'm going to be in the steady state, so that doesn't matter. There is no commutator. I'm going to have n in here as the argument, but I also want to look at the diagonal part of that. Okay, so I have to take the band diagonal part of this. Right, so I take the band diagonal part of this, and I end up with this Fermi's golden rule thing here. Right, and then whatever I get on the right-hand side, I don't, well, that's just a driving term. So that just stays there, and I, multiply something by it. All right, so for n, basically what I have to solve is the Boltzmann equation. There's a slightly different driving term because there was that JE there, but J is a correction. All right, so the commutator drops out, and I have to solve this J diagonal acting on NE, and that is equal to my standard driving term. It basically drops, it basically breaks down into this Boltzmann equation for each band. And NE is going to be order -1 in this small parameter, so h bar over E of tau, for the reasons that we discussed. Okay, and this is going to give exactly the same correction to the distribution function. The distribution function for each band, it's exactly the same correction that we got by solving the Boltzmann equation. So what happens to the interband term? So the interband term, you get a time derivative. Apologies, this should be a partial, but this is from an older slide. There's the commutator term, which is straightforward to deal with, and then there is a driving term which I get from the intrinsic. So actually, this is the intrinsic part of the driving term that I discussed on an earlier slide. And then I get this correction, which is essentially where all the unconventional sort of disorder dynamics comes from. So the key here is that whereas the n starts at order -1 in disorder, okay, S has to start at order 0 because you have this commutator. All right, and if you don't believe me, you can simply use some relaxation time approximation. You can solve this equation in a minute, okay, with an integrating factor, and you'll see that in the limit in which tau is long. So again, it's semi-classical limit E of tau over h bar is large. Okay, the dominant term, the leading term is order 0 in disorder. However, there are two ways we can get something of order 0 in disorder. One of them is intrinsic, so it has nothing to do with disorder. The other one is we have already solved for NE, and NE is order -1. And I take the NE of order -1, I plug it into the scattering term, I get something of order 0. And then from that something of order 0, I select the off-diagonal part, and the off-diagonal part acts as a driving term in this equation. Right? This is what we called, for lack of a better term, we called it the anomalous driving term. Right? Because it comes from n, it comes from the Fermi surface, and this is what kills, this is what gives us agreement with all the Kubo formula evaluations. All right, so it kills the spin Hall effect, the anomalous Hall effect in the Rashba model. And so basically, we now have three main contributions in the density matrix. There's a band diagonal part. So that one is just a straightforward picture where the electric field is accelerating electrons in this thing. It gives you a driving term, and then scattering balances that acceleration. There's a band diagonal part, which has nothing to do with scattering. And it gives you these properties that come from the entire Fermi sea. At least formally, the first, they appear to come from the entire Fermi sea. And then there's the second off-diagonal contribution, which is it's a contribution. It's a correction that's coming from disorder, and it's a correction that is formally of order 0 in disorder. So this usually competes with the intrinsic term, and we've actually checked that this corresponds to the vertex corrections in the Kubo formalism. So there's 3 things that need to be taken into account. So finally, how do we go from this density matrix approach to the semi-classical approach? So we have, and this is the insight that I had maybe 2 years ago or so. So disorder gives you these, they gives you these band mixing effects, and you don't get the band mixing effects that captured by a naive application of the Boltzmann equation. Now you might say, I take the Boltzmann equation and I can write down a Boltzmann equation for each band. And when you do that, of course, you can incorporate scattering between the bands. Okay, you can have an intra-band scattering term and an interband scattering term, but that is not enough, because the disorder also changes, it includes changes, gives you changes to the particle dynamics. So it's not just scattering from one point on the Fermi surface to another point on the Fermi surface, which you can include at the Boltzmann level. Okay, there are changes to the particle dynamics, and these changes are something that you cannot incorporate at the level of the wave function. Okay, to make sense of, and the only way we can make sense of it is to average over disorder, and we can't average over disorder at the level of the wave function. Okay, so what we thought was, we can you take the density matrix as our starting point. Okay, start with the full, quantum mechanics, and we average over disorder, and then we derive the semi-classical equations from the density matrix, which has already been averaged over disorder. All right. So K, if we start at the full quantum mechanical operator level, right, and we have, we simply take the Hamiltonian, let's say it's EE dot R, and you take K dot. K dot is going to be just the operator equation. That part is quite trivial, because you have K commutator with R, and that just a constant, and then there's the EE multiplying that outside, and you get K dot is minus E over H bar immediately. Now, all the complication is getting R dot. So to get R dots, we want to take the density matrix and trace the velocity with the density matrix. But we can't do it if we want to recover the semi-classical dynamics. We're not going to do it in exactly the same way that we did it in the density matrix, because there's nothing new there. Okay. However, I'll explain that in a minute. Obviously, we're going to talk about disorder averaging. Then we need to change our point of view somewhat. So in the semi-classical, traditional semi-classical approach, we have propagation between scattering events. Okay, but if we're going to come up with some modified equations that are averaged over disorder, then these will describe particle propagation averaged over many scattering events. Okay, so as the particle propagates, right, it will undergo some transitions between the bands, and so essentially disorder is going to lead to some admixture in the wave function. All right, and the trajectory is going to be determined by taking whatever we get and averaging over some impurity configuration, over impurity configurations. So there's going to be modifications to the Boltzmann equation as well, but that part is more straightforward. So the results, okay, so I'm going to explain how I got this. I'm not going to just throw this on here, because this is why we're having this meeting. But the result is that at the end of the day, we have this R dot. Okay, we have the group velocity, we have the Berry curvature term, and then we have an extra correction to it. And this extra correction, this beta, is what we call the extrinsic velocity. Some people have argued that it's basically what you'd call the side jump velocity. Okay, I prefer to call it extrinsic velocity. It's a vector and it depends on disorder. All right, so this beta has a very, very similar form to the scattering term. I'm writing it now in terms of, you know, this epsilon is just the Fourier transform of the time variable. So it's like some energy variable, which, because it's more convenient to do it this way. All right, but you see that these GA and GR, so they are the advanced and retarded Green's functions as a function of energy. Those are just the Fourier transforms of the time evolution operator. And in this second commutator, in this inner commutator here, instead of having rho, where we had the density matrix, now we get this Berry connection. And it's because there's a prime. The prime says that only the interband matrix elements of this R appear. So this beta, because it goes as U squared, it's proportional to the disorder strength. So it would be proportional to n impurity, or, you know, more generally, it's going to go as 1 over tau if we use tau to parameterize disorder. So now if we go back to the simple semi-classical approach, where we work out the wave packet dynamics and trace it with the distribution function, then if this goes as 1 over tau and the f is linear in tau, then the result behaves as if it's disorder independent. And this will entirely reproduce the effect of the anomalous driving term. And it does that because we have designed it, you know, to be this way. So how did we do it, right? So how do we do it? This is basically the missing link that was missing for so many years, right? So first of all, we're going to do the quantum mechanical thing. We're going to, okay. So we'll take the distribution function, not distribution, the density matrix. Apologies, there's a slight change in notation here. The F is the row brackets. Okay, so I've decided to simplify this here and stick to the notation in the paper. So we trace R dot. Now R dot is the position operator. The position operator is just the commutator of H0 with the, sorry, is the velocity operator. The velocity operator is the time derivative of the position operator. And quantum mechanically, that's just a commutator of H0 with R. So we trace this, right? Again, insert complete sets of states, deal with the position operator, etc., etc. And we will get, we'll get a group velocity, then we get the energy difference multiplied by the Berry connection, and this is all multiplying the density matrix. And then we write the density matrix in terms of a scalar of the band diagonal part and the interband part, which is the S. Okay, so I mean, there's no magic here. There is no magic in going from the first line to the second line. Okay, Vm is just a group velocity. That's this dE dk with the h bar. And then we say the n is going to have, of course, there is, there's going to be NE will have a contribution from that is -1 order, -1 in disorder. There will also be a contribution that is 0th order in disorder. And this I just get simply by taking the Boltzmann equation and solving, going just to the next level, okay, which I can do again at the level of the Boltzmann equation. And I have this other contribution, this interband contribution S, right? And I basically have to figure out what to do with this, right? This is where the you know, I have to do some extra thinking, because the reasoning of the wave packet formalism, you know, is that I have some wave packet dynamics and I multiply it by some distribution function. Okay, and this distribution function, if I'm going to talk about wave packet dynamics in a certain band, right? And I'll remind you that here I am in one band. Okay, beta contains the effect of the other bands, mediated by, the disorder couplings to the other bands, but I've designed it in such a way that I can define this extrinsic velocity for a single band. So whatever I multiply it with, whatever I trace it with, had better be a distribution function. So it had better be band diagonal. Now, these terms are band diagonal by construction. Yeah, -1 in disorder, 0th order in disorder doesn't matter because I can get that purely from the Boltzmann equation. Right? I have this interband term as 0, and I need to do something with it because I don't want to deal with interband contributions. Otherwise, I can't talk about semiclassics. So of course, this has two parts. Okay, so if you remember the solution, we had two driving terms. One of them was this. One of them was the intrinsic part, which came purely from, again, it had another factor of the Berry connection. All right, so this was the one that had the Berry connection, and then F Fermi-Dirac for band M prime minus F Fermi-Dirac for band M. So that's nice because it only contains F Fermi-Dirac, and F Fermi-Dirac is band diagonal. So if I take the trace of this with R dot, so basically these guys here, right, I can rearrange these, I can take the trace blindly, and I can rearrange the terms so that I only deal with band diagonal quantities. Okay, this takes a bit of work, but it's shown in the paper. And this is also very well known. So there is nothing that we did here that was new, right? And you rearrange it and you get E cross omega times the Fermi-Dirac distribution. And then you just sum over bands. So then I can simply say, again, yeah, I can simply focus on each band. And I say that I have E times the Berry curvature for the band multiplied by the equilibrium distribution for each band. So then again, I can say that the part that comes from the left, from this cross product, is the carrier dynamics, and this part here is the distribution function. Now, the other thing that we have, the extra contribution, and again, this is basically the crux of it all, is we have this anomalous driving term. Okay, so okay, the extrinsic or anomalous driving term, and this extrinsic driving term is written in terms of, this is the one where you kind of iterate, you have to do certain, a number of things to get to, right? And this is basically the scattering term J that acts on any order -1. Okay, NE being basically the diagonal correction to the density matrix, which is like the diagonal correction to the Boltzmann distribution. So again, this is order 0 in disorder. All right, so I take this trace, and again, because this all comes from NE, and NE is band diagonal, I can write it as the product of two band diagonal quantities. So one of them is simply the correction to the Boltzmann distribution, and the other one is something else, and that something else is what we called beta. All right, and then, sorry, the beta is defined here. So we were able, because ultimately, there are two important things here. Ultimately, we're doing linear response, so we do start from the equilibrium distribution, and the equilibrium distribution is band diagonal. Secondly, the correction, this NE, the leading order correction is when you're in an electric field, the leading order correction to the density matrix is the band diagonal correction. Okay, so then we were able to recast everything in terms of these band diagonal terms. So band diagonal density matrix, and a band diagonal effective velocity. And in this effective velocity, we were able to lump the effect of this scattering of, or essentially the effect of the disorder, sorry, not the scattering, but the disorder potential on, interband dynamics. Really what this means is there is an admixture of, so in addition to just interband scattering, there is an admixture of the other bands which is induced by the presence of disorder. Okay, and that admixture we can write as an extrinsic contribution to the carrier velocity. There is, if you want to do it properly, so that was one thing. So that was my realization. And then, I talked to Ronald Burgos and I said, it's time to, see how we reproduce the semi-classical results completely. And Ronald found out that we actually need to make this, we need to consider this correction to the diagonal part of the density matrix that is also of zeroth order in disorder, and for that you need to do some additional algebra. But this is ultimately it's ultimately the reasonably boring algebra. Okay, so we kept ultimately what we did, right? Is we kept the scalar part. So to get this, the semi-classical dynamics, the carrier dynamics, right? We kept the scalar parts and reformulated the density matrix theory in such a way as to get rid of the interband part. So we took the interband part and we expressed it in terms of single band quantities. The intrinsic part gives the Berry curvature, the extrinsic part gives this extrinsic velocity. Right, S is the term that represents, it's like either spin charge coupling or pseudo spin charge coupling. So it's like a feedback effect of the spin dynamics on the charge dynamics. And the example that I like to give is an intuitive example, right? And this again is mostly for the intrinsic part, but I think the picture is useful. You take a spin orbit coupled system like Rashba, where the spin is coupled to the wave vector. Okay, you accelerate the particle, you change the wave vector. When the wave vector changes, you get a spin rotation. And the spin rotation in turn will give you an additional change in the wave vector. And so it will give you additional charge dynamics. For example, the anomalous Hall effect. And if you want to look at the effect of scattering on this, you think that the scattering will rotate the spin. And it rotates the spin because you scatter from one wave vector to another. You go to a new wave vector, then the spin will be rotated, right, to that new wave vector, to that new direction. So there's a sequence of random spin rotations, and these random spin rotations have an additional effect on the charge dynamics. And ultimately, I wanted to point out that all these theories come from the same starting point. So you can start with the quantum Liouville equation. You can go to Kubo by using an integral approach. You can go to the quantum Boltzmann equation by using a differential approach. So let's say Keldysh. Or you can also derive a quantum kinetic equation, just sticking to the density matrix. So it's another differential approach. And then at least for certain dynamics, you can separate the dynamics and the distribution and recover this semi-classical model. So that is basically my summary. It's obviously taken longer than I had intended, but yeah, this is the end. So for those of you who've lasted this far, thanks a lot.
Thank you very much. I think your timing is perfect. I gave you 90 minutes. You filled 90 minutes. So let me stop recording.